Hi there. Today I'm going to teach you an expression. Or really, I'm going to mispronounce something, or so you will think. And that is, here, I want you to say out loud, what do you think that first word says? Yeah, you probably said arithmetic, which is a noun. And if you look at what this is here, it's describing a certain type of sequence, which means it's actually an adjective. And so instead of saying arithmetic sequence, we need to say arithmetic. Now, can you say that? I'll say it and then you say it. Arithmetic. Yes, arithmetic. Okay, one more time. Arithmetic. Alrighty then. So it's an adjective. It's describing a certain kind of sequence. And we're going to be doing integers today, a sequence of integers. A sequence is just one number and then another number and another number, and that there being some rule that tells us what the next number is going to be. It's kind of like a game. In fact, some people it's not a game. Some people this is serious business. Okay, so there's a guy, Dr. Sloan, and he has developed a website, a foundation called the OEIS. Okay, and OEIS stands for Online Encyclopedia of Integer Sequences. He's cataloged thousands of different sequences and then tells you what the sequence is and then describes the rule that makes that thing happen. Sometimes there's a coding that you have to do to put it into to write a program to generate them. Sometimes he'll draw the pictures out. If you're watching a number file video, he's highlighted quite a few different sequences. And there are lots of different kinds of sequences out there. One of the most famous sequences is the Fibonacci sequence, where I guess depending on who you are, you might start off with the numbers 1 and 1, and then what you do is you add the two previous numbers to get the next one. So 1 plus 1 is 2. And then this one comes from adding up the two previous numbers. 1 and 2 makes 3, and then 2 and 3 makes 5. The next one would be 5 and 3 makes 8, and then that one just keeps going. That one's really super cool. Not just it's really easy to write, but it has a lot of cool mathematical properties, and you find it in lots of different mathematical objects. It's all good fun. Fibonacci. Fibonacci. Let me have you draw this one, okay? Let's imagine that we've got some square tables, and we're setting up for some dinner or something, and we want to know if we're going to put all these square tables next to each other, how many people can we get? How many chairs can we get around these tables? So let's just start off if we got one table. Obviously, you can sit 1, 2, 3, 4. There's 4 places where a person can sit with one table. Now, if we add a table, we're just going to put that table right next to this one. Of course, there's a problem now. Nobody can sit right there, but people can sit here. So altogether, you got 1, 2, 3, 4, 5, 6 people that can sit around 2 tables. Okay? And if we add a third table, we take away that 1 seat and we add 3 seats. So altogether, we got 3, 4, 5, 6, 7, 8. Now, what you should do here at this point is be able to make a prediction as to what is the next number. If I add another table, how many more people can I get to sit here? And the pattern is already pretty obvious. 4, 6, 8. What should the next number be? Picture-wise, we can see that we take away 1 and we add 3, right? So really, we're only adding 2 to the next one. We get 10 on our these above them when we got 4 tables. So we could draw a picture to describe the arithmetic sequence, but we could also come up with a formula then once we've kind of seen the pattern. We start off with 4, and then every table after that, we're basically taking away 1 and adding 3. take away 1 and we add 3 every time we have another table. Okay, so we could say this too. We could say, well, basically the number goes up by 2, but the number is only going to go up by 2 when we're at the next table. If I put in a 1 for the first table, that makes 0. 0 times 2 is 0, plus 4 would be 4. The next one would be, I put in for the second table, how many people would be sitting there. That makes it 2 minus 1 is 1 times 2 plus 4 is 6. So this is one way of writing that rule, but I could write that rule in lots of different ways in order to generate the next one. Actually, I could use this formula, once I found the pattern, to say what if I put 18 tables together in this manner, what would be the number? And we'll talk about that in a bit, what kind of formula that is that can generate any place along the sequence that you want to, or if you are just finding the very next number in the sequence, the formula that fits for that. So we call this arithmetic, okay? Arithmetic because it has to do with adding another number on top of the first one. With each of these, we could go from the first one to the second and say, get to the first to the second, second to the third, and third to the fourth. We have a common difference of 2. We add 2, we add 2, we add 2 every single time to get to the next term. That plus 2 in this problem gets the letter D that goes with it for common difference. And every arithmetic sequence has a common difference. Arithmetic sequences are very simple. All you have to do is find the same number that each value is away from the next one. Leads me to give you what's called a recursive formula. A recursive formula just helps you generate the very next term. So let me write this thing out for you. Okay, and then describe what we got here. This right here is called the nth term. So if we put in a 2 there, that would be the second term. If we put in a 3 there, it would be the third term. Okay? What you need, though, is the term that came right before it. That's what this one is right here. And the subscripts are not like exponents. It's not an operation. It's just a way of naming that particular term. In our sequence up here, 4, 6, 8, and 10 were all terms. 4 was the first term, 6 the second term, 8 the third term, 10 the fourth term. So this one represents the one that comes right before that term. We'll call it the previous term. And then there's our common difference. So we need what's called like a seed. Okay, we need a seed term. We need to plug something into this, add the common difference, and then a new number comes out. And then we put that seed back into the machine, add our common difference, and a new number comes out. With this problem right here, if we were looking for the third term, a of 3, a sub 3, we would need to know what was the previous term, and if we had that second term is 6, we found out that our common difference is 2, and means that A3 is 8. Okay, that's called a recursive formula because you need the one that came right before it to figure out what the next one is. And there you need the one that comes before it, and you need to know how far apart each number is from each other. Okay? That one's pretty straightforward, right? We could keep following that all the way to however far we want to go. 2, 4, 6, 8, 10, 12, whatever. We could keep going forever and ever. Amen. Okay, but what if you don't want to have to go through every single one of them and to find maybe you want to find the 100th term? There's a way to do that if you know certain information, and that is called using an explicit formula. An explicit formula looks like this. We have again a sub n, which means whichever term that we want, the nth term. And this time we need to know what's the very first term. And then we get this funny little formula here. Do you remember this thing in the last one right there, n minus 1? It talked about basically about the previous thing. But here, n stands for the number of things, or the index here that we want to find. Maybe we want to find the 15th one. Well, we'd say a sub 15 equals the very first number in the series sequence, and then we put 15 right there. And d, again, stands for our common difference. Find all these terms in the book. There's the very first term. There's the nth term I'm looking for, and difference. So in our example up here, the very first term is 4. And then we're going to add to that. Well, let's say we want to find the 100th term here. We're going to go 100 minus 1 times our common difference of 2. Now, why do we do it 99 times, right? Why do we do this 99 times rather than 100? Because we're finding the 100th term. Because there's our first one, right? The first one starts at 4. And then on the second term, we've added 2 once. On the third term, we've added 2 twice. And on the fourth term, we've added 2 to the original number 3 times. So we're finding how many times have I added 2 to this problem. That's what this explicit formula would say. So we say, well, we've done this 99 times. We double that, that would be 198. Add on that original 4, and we get that the 100th term would have to be 202. So in the first case, we needed to know what was the one that came before it and the common difference. And for the explicit formula, we need to know what's the first one, what nth term are we looking for, and what is the common difference. We're going to use 1 in one case and 1 in another. Sometimes they want to know if something actually is a arithmetic sequence. And it's only an arithmetic sequence if we have common difference. Okay, so I could write a sequence of 3, 6, 9, 13, 15, and we would see that that's not arithmetic. Must be some other thing going on, because this one goes up by 3, and then up by 4, and then up by 2, and it has to be the same exact number every single time for it to be an arithmetic sequence. So the book's going to ask you to determine whether or not something is arithmetic or not. Let me pause and look at a couple problems. We only have a couple minutes left to knock some stuff out, so hang on. Okay, let me give you one of each to think about here to have a pattern to follow. And then what I want you to do is to bring to class one interesting sequence that you found. If you've gone and go and visit oeis.org, find one interesting sequence and tell me about it. But the first question here is, if they say that the first term in a sequence is -2 and the common difference is 5, they want you to say generate the next 6 terms or something like that. Okay, so A1, they want several terms here. A6, let's say like that. And then we already got the first one, -2. And then we say, what's the common difference there? And we go up by 5, and then up by 5, and on down the line. Okay, so I bet you could do that if you're given the first term and the common difference. And then let me do another one here. Okay, on this one, they want to know what is the 10th term, A sub 10. And they give you the sequence. They give you the first 4, but they say, what's the 10th thing? You could just go ahead and keep the pattern going and list them all out, or you can use your explicit formula and find the whole thing. So what do we need here? We need the first one, right? A sub 10 equals the first term, which is 2, plus we want the 10th term, so we're going to plug in a 10 there, and we need a common difference. Can you see the common difference in the problem? How far apart are they from each other? Looks like they are 15 apart from each other. So there you've got your little formula to go off of, and you do the math, and you'll get 9 times 15 plus 2 will be the 10th term. So you can double check by keep adding 15 on down until you get to the 10th one, but that formula right there will get you the right answer right away. Use your calculator. It's fun.